friends. So this is Sarvachalam, Assistant Professor in Chemistry, Bishopur College, Trichy. In this video, I am going to discuss with the quantum chemistry, in which we are going to apply the Schrodinger wave equation to particle in a one-dimensional box. This is the simplest quantum mechanical problem. The particle of mass m is restricted to move in one-dimensional box of length a, having infinite high walls. Assume that the potential energy is 0 inside the box. The Schrodinger wave equation dou squared psi divided by dou x squared plus 8 pi squared m divided by h squared e minus v into psi is equal to 0. So when you apply the potential energy inside the box is equal to 0, so the equation is modified with dou squared psi divided by dou x squared plus 8 pi squared m divided by h squared into e is equal to 0. Since pi, m, h are constant, we may put as k squared. The equation now dou squared psi divided by dou x squared plus k squared psi is equal to 0. So when we solve this equation using the boundary condition, when psi is equal to 0 at x equal to 0, the second one, when psi is equal to 0 at x equal to a, it means at the walls there is no wave nature. So the general solution for psi is equal to a sin kx plus b cos kx. After applying the boundary condition to the general solution, we receive a solution for psi is equal to a sin n pi x by a, where a is here the amplitude of the wave function or the normalization constant, and the energy of the particle also solved using the above Schrodinger wave equation as E is equal to n squared h squared divided by 8 m a square, where h is the Planck's constant and n is the quantum number, a is the total length of the box. The quantum number varying from 1, 2, 3, 4 and so on. So there are three physical principles can be understood from the system that we discussed here. One is the quantization of energy, second one is the quantization of momentum, the third one is uncertainty principle. So the separation between any two energy level is quantized, denoted by delta E is given as 2n plus 1 h squared divided by 8 m a square. From this equation, we may see that when the quantum number is very high, the quantization also is larger. And if the length of the box is become infinite, the quantization is vanished. It means the energy is not quantized, the energy is continuous. And then the momentum also is quantized as nh by 2a. Again, the quantization of momentum is more pronounced at high quantum number and became continuous if the length of the box is became infinite. The third one, the Heisenberg uncertainty principle, has very good agreement with the calculation of position and momentum gives in the integral multiple of h, which is Planck's constant. So the magnitude of uncertainty is also proportional to the quantum number.